Good morning. So, welcome to this lecture in our course on mechanical operations. As I mentioned in my last class, introductory class, while there are many varieties of mechanical operations, there are certain things that are common to all of them, and that is the properties or characteristics of particles which affect the efficiency of these processes. So, as an example, there is a mechanical operation that you are probably familiar with even from school, sieving, screening. I am sure you study those things, and I have seen those in your 11th standard, 12th standard textbooks. How does it work when you use a sieve to separate particles by size? What does a sieve look like? It's got a lot of meshes, right? Square shaped meshes, and you stack the meshes in such a way that the coarsest mesh is at the top, and then the meshes get finer and finer as you go down the stack. The idea is quite simple. You take the powder that you are trying to size separate, put it in the top sieve, shake it, and particles whose diameter is smaller than the mesh size will fall through and go to the next sieve, and so on. So, you can separate the particles by size. The finest particles will go through the bottom mesh and be collected in a pan or something. Now, that sounds simple, but do you think it will always work? What is the primary requirement for sieving to be effective? What is the primary assumption you are making? That the particles are spherical in shape, that they have a definable diameter which you can then correlate versus the mesh size and say that, you know, if your particle size is the diameter is smaller than the mesh size, it will go through, and if it is larger, it will not. The mechanism here is called interception. Again, we will talk about this in more detail later on, but interception requires trapping of a particle because its size exceeds the size of an opening that is available to it. Now, if all the particles were spherical, this will work perfectly fine, but suppose you have particles in your powder that are not spherical. Let us say that some of them are elongated, very high aspect ratio. Then what happens? As the particle approaches the mesh, its orientation at the time of approach will decide if it gets trapped or not, right? If it comes in a flat configuration, it will get trapped even in the coarsest mesh, whereas if it comes in a vertical configuration, it will pass through even the finest mesh, right? So, you are clearly not going to be able to achieve effective separation by using the meshes in sieving apparatus or screens and so on. Even another example, you have all again studied sedimentation in various contexts earlier on. Sedimentation refers to settling of particles, and again people use settlers as a way of separating particles by size and mass and so on. The idea here is that different particles will settle at different rates, and so if you have a setup where you can decant the liquid at various levels, you can actually separate the particles by size based on their settling characteristics. Here again, the major assumption that you are making is that all particles are reasonably uniform in shape and that they are all spherical in shape. Here also you can imagine that if you have a non-spherical particle, its rate of settling will very much depend on its orientation, whether in water or in air. You know, you think about a fiber that is floating in air, its residence time can be very long, because if it presents a large surface area for the wind resistance, whereas if it happens to fall, you know, edgewise, then it can fall very rapidly. So, shape can have a huge influence on the effectiveness of many mechanical operations, because most of our equipment processes are all defined or designed with the assumption of sphericity, and if that assumption is violated, pretty much all bets are off. You know, nobody knows how non-spherical particles behave. It can be a very chaotic situation where, you know, the behavior from one moment to the next cannot be predicted if you have an assembly of non-spherical particles. So, given all that, it is clearly important for someone who's designing a mechanical operation to understand the shape distribution of a population of particles, just as it is important to understand the size distribution. So, shape and size, as I mentioned in the last class, are the two most basic morphological parameters characterizing a particle, and frequently they are defined together. But what is the difference between them? Well, shape is essentially a qualitative parameter. You can try and quantify it, but if you do, you have to refer to size dimensions again, or you have to use purely verbal descriptions, rod like, disc like, needle like. It is either that or you use size parameters as a quantitative way of defining shape. Shape is unique, it is like the fingerprint of a human being. Every particle has a different shape, even a spherical particle. The reason for that is that shape refers to essentially the external profile or pattern of a material, right. It is a reflection of how the volume of material is packed in, or the mass of material is packed into a certain volume. But shape, even though it refers to the external surface, the surface itself is not a 2-dimensional parameter, it is actually 3-dimensional, because there is always a surface roughness associated with the external surface of a particle. So, that gives it the 3rd dimension, and that is why virtually every shape is unique, because even though it may be a sphere, the 3rd dimension, the roughness dimension, may be has to be very different. It cannot be the same between any two particles. So, the fact is that shape is a unique parameter. It is an intrinsic parameter. What do we mean by that? Extrinsic parameters are additive in nature. For example, you can say that if you take particle 1 of size A and particle 2 of size B and you put them next to each other, then the total size of this assembly is now A plus B, right. But in terms of shape, can you say that if you take particle 1 of say spherical shape and you take another particle of spherical shape, shape is not additive, right. It actually depends once again on the way that you pack these two particles together. So, you can take two spherical particles and assemble them in such a way that the resulting particle is also a sphere. I mean, certainly you can imagine that if you have liquid particles, liquid drops, two spherical liquid drops will get together to make a larger sphere, but you cannot always say that. So, shape is not an additive property, it is not a subtractive property, so it is called an intrinsic property. Shape again refers to the external contours of a particle. In a way, shape definition is a pattern recognition exercise. Now, pattern recognition is something that is used in many fields. Increasingly, there are many apps that run via pattern recognition. Now, when you do a Google search and you do images, how does that work? It basically tries to match the pattern. If you are looking for a particular person and you do an image search in Google, what it does is it digitizes that person's image and then it searches for similar images in its library. That is basically pattern recognition, right. Shape analysis is also a pattern recognition exercise, and it is very interesting that the human eye is capable of understanding shape billion times faster than the fastest computer ever built. For example, that bottle I brought, any human being will look at it and immediately say that is a bottle, but for a computer to say that it is a bottle will require extensive computations, because shape again is an intuitive parameter. It is something that we have learned to recognize over time because of the experience that we have gathered over our lifetime, and that is very different from size. When you talk about size computation, in many cases a computer or an automated device may be a lot faster than the human eye, because the human eye cannot quantify precisely, but it is very good at qualitative characterization, right. So, shape and size are very aligned properties, but they have distinct differences. So, how do you measure shape? Well, there is actually 3 important steps in measuring shape. The first is data gathering, the second is data analysis, and the third is the judgment process. By the way, the lecture that I am going to give today, I hope I have time to complete it, is a summary of 3 lectures that are in my NPTEL course on particle characterization. Again, if you go to YouTube and type YouTube Nagarajan particle characterization, it will bring up the course. Lectures 3, 4 and 5 are related to shape characterization. So, please use that as your reference material, because I am not going to be able to cover in this course in as much detail as I have covered in that course. So, data gathering. Then we have data analysis. The third, as I mentioned, is the judgment process. So, when we talk about data gathering for shape, the simplest method to do that is basically just take one data point and use that to represent the shape. Now, is that a valid approach? Well, that is what we used to do. The thing that has happened in the last few years is that our computational capabilities have increased exponentially, but even 40 years ago, 50 years ago, our ability to collect data and store data was very limited, right. So, people try to minimize the amount of data they took in any application. So, if you have a random particle and you are trying to decide what shape it is, the simplest thing you can do is look at it optically, either just gross visual inspection or under a optical microscope, and look at its most characteristic dimension. Could be the largest dimension, could be an average dimension, but you try to represent shape by a single data point. So, for any particle you just collect one data point. Now, the more sophisticated variant on that is to take 2 data points, where you take say one primary dimension and then you take another dimension that is perpendicular to it, right. So, you represent the shape of the particle as that of a 2-dimensional object, which is characterized by these 2 dimensions in orthogonal directions. That again was the first improvement that people came up with. For example, you could call the longest dimension length, and you could call the orthogonal direction width or breadth, and you take the ratio between the 2, call it the elongation ratio, and use the elongation ratio as a representation of the shape of the particle. Now, what we do is we are now able to, and therefore we do collect many data points. So, if the Mars rover brought you a particle from the Mars surface and you want to characterize its shape because it is very odd, what a scientist today would do is not even care. He will just stick it into a automated scanner which will digitize the profile of the particle and take billions of data points, so that you have the information in digital form. So, you have the digital profile of the particle, and this digital data set can then be manipulated in several ways. It can be used as discrete digitized data points, or you can fit a polynomial to it, or you can do Fourier analysis. There are many ways you can manipulate the data, but the point is the data gathering part has now become something that is entirely at our disposal. It just depends on what we want, right, because the computational ability is there, the visualization ability is there, so there are no constraints. Now, data analysis. What do you do with the data once you have taken it? The simplest thing you can do is to simply record it. So, you have an observation book and you just write down particle XXX, and this is the shape that I observe, which is fine. I mean it enables you to record the actual observation. What it does not provide you is the ability to provide a historical database, in the sense that you are able to go and compare this with prior observations and look for commonalities, common features, etc., so that you use your developed knowledge to ascribe a shape to the new particle that you are looking at. So, the next iteration on this is tabulation of the data. So, tabulation enables you to keep the data in a chronological way. It also enables you to measure multiple data points from a particle and record it in the form of a table, and of course the extension of that is graphical representations of the same data. So, whether you tabulate or graph, it's an additional sophistication in your shape analysis process. And then the third part, or again what is done today, is mathematical analysis and digitization, curve fitting, and so on. So, in terms of level of complexity, just as going from one data point per particle to many increases complexity by several orders of magnitude, so does in the case of data analysis simple recording of data versus actually manipulating the data and drawing statistical inferences from the data as well. Now, the third part is actually the most critical, and here is where we have a huge advantage over a robot or a computer or any automated imaging system. With minimal data, a human being is able to ascribe shape very precisely and very clearly, whereas a computer would require a lot more data to be able to do the same thing. So, the judgment process, what is our main objective? Our main objective, and this is something that a person by the name of Hausner stated back in the 20th century, it is called the Hausner postulate. The question he was presented with is, how much data do you need to characterize shape? And he said the amount of data collected should be sufficient that the observer can recreate the shape of the particle in such a way that it satisfies the observer's functional requirements. In other words, what he is saying is that shape is essentially in the eyes of the beholder. There is no definition of a precise shape. You only want to achieve as much precision in your shape definition as is necessary for your application. Do not overdo it. Why is that? Have you heard of the law of diminishing returns? Who has not heard of the law of diminishing returns? So, the law of diminishing returns basically says that in any exercise, when you put some effort into something, you get a result, right? You put more effort, you get more results, but it does not continue linearly. You reach a point where additional effort does not really give you additional information. There is a plateauing that happens. Graphically, we can represent it in the following way. So, let us say that you plot effort in some way and outcome in some way. Initially, for even a little bit of effort, you get a lot of data, lot of information, lot of insight. So, it kind of goes like this, but then it starts leveling off, and you reach a point where additional investment of effort does not really pay you back that much. So, if you are smart, what would you do? You would stop your data collection exercise, somewhere here, right? Because that is where you have the maximum bang for the buck, so to speak. Putting in additional effort does not buy you much. The other thing you have to also keep in mind is that there is another axis to this curve, and that is cost. The additional effort that you are putting in is not free, it comes at some cost. How would the cost curve look, effort versus cost? Do you think it will be a mirror image of this? Do you think it will be same as this? So, let me give you 3. So, suppose you plot cost on this axis versus effort. Do you think it will be linear, or do you think it will follow a pattern like this, or do you think it will be more like this? Let us say this is 1, 2, 3. How many people vote for 1? 2, 3? Okay, so you get the point that it's a double penalty. Additional effort doesn't only get you less and less results as you invest that additional time and effort, it also costs you more and more, and therefore it again argues in favor of understanding exactly how much data you need and stopping your data gathering and data analysis effort at that point. Now, it may be that even this, let us say 10% additional input or outcome or data is important to you. I mean, if you are a scientist, and as I was saying, you are studying some extraterrestrial particle, you are willing to make that investment of additional effort, additional cost, even to get that very incremental bit of information. But in most commercial applications, if you are just running a factory and you just want to know approximately what is the shape distribution of this powder that I have, I am sure you will stop way before this inflection point, and that is where you have to exercise your judgment, and that is where a robot would not know where to stop. A human being would know very clearly how much effort is enough, how much data is enough. Okay. So, in shape analysis, it is a truism that the more you work on it, the better, the crisper, the more precise will be your definition of shape, but you have to exercise your discretion to decide when to stop the analysis. All right. Okay. Now, when we talk about shape analysis, what are the different classes of methods of shape analysis? Now, these can be broadly subdivided into 4 categories. The first is based on single particle analysis. The second is based on bulk powder properties, bulk powder analysis. The third is based on mathematical techniques. And the fourth is based on verbal descriptors. So, when you have particles, you are very rarely going to be looking at single isolated particles. What you will have is a set or assemblage or population or powder of particles. So, when you do shape analysis, you have a very simple choice to make. You can choose to do the analysis of one particle at a time. It is called the single particle approach, or you can say, I do not really care what the individual shape of an individual particle is, I just want to know the overall shape distribution of this population, so that I can predict how it will behave in my process. In which case, you do not even have to do the single particle analysis. You can just look at how that entire powder behaves and derive relevant information about shape. It goes back to this judgment process. You have to decide whether single particle analysis is justified or it is an overkill. So, mathematical techniques, again, now that we have the ability to collect lots and lots of data, we can always choose to very precisely and mathematically describe the shape of a particle, but we have to decide whether that is necessary or not. And finally, verbal descriptors. Verbal descriptors are important because frequently you have to communicate across labs, across manufacturing locations regarding what you think the shape is. So, in that situation, if you are able to come up with a simple verbal description of the shape of the particle, it makes the communication process a lot more effective than if you just try to represent everything in numbers. So, these are the 4 major categories of shape classification, and each one can be subclassified further. For example, when we talk about single particle characterization, there are 3 major types of single particle characterization. One is based on distance between tangents, that second is based on lengths of intercepts, third is based on shape comparators. So, when you look at a single particle and you are trying to ascribe shape to it, how do you do it? So, the typical approach of an analyst would be to put it on a microscope stage, align the eyepiece, then what do you do? Again, you have to remember that when shape analysis started as a science, we did not have access to the kind of sophisticated instruments, the kind of high magnifications, the kind of high resolution that we have today. So, they had to work essentially with optical instruments, not laser based instruments, and they had to limit the amount of data that they took. So, the first approach, distance between tangents, is simply saying that you take the profile of the particle and draw parallel tangents to it at its contours and measure the distance between them. Okay. So, that is a very simple representation of the shape of a particle. So, if you have a particle that looks like this, you would draw 2 tangents here and measure the distance between them. You will draw a couple of tangents here, measure the distance between them, and you keep doing this over and over until you develop sufficient confidence in your data that you have captured all the essential features of the shape of the particle. So, the distance between parallel tangents is was the first quantitative measure of shape, and as I was mentioning, as soon as you try to quantify shape, what you are really talking about is size, right. What you can do is, once you complete this exercise, let us say you have measured these distances between tangents in 50 different directions, angles. You can look at the distribution of these distances, and if they are roughly equal, then you would say it is a spherical particle. But if these distances between tangents are very different, you would say that it is a highly non-spherical particle. So, sphericity can actually be inferred from these measurements, and that can be presented as a qualitative measure of shape. The second one, length of intercept, it is more for a 3-dimensional object, and the idea is that when you have a 3D object, let us say that you take a dot and you throw it at the object. How far does the dot penetrate into the object before it comes to a stop? In other words, what is the length of the interception of this dot with the object that you have? So, you can kind of imagine that it is a way of measuring the 3-dimensional shape of an object. So, the bulkier a particle, the longer will be the intercept, right. The needle or dart or whatever you throw will be able to penetrate deeper into the object before it reaches the other side. So, bulkiness can be measured using this type of length of intercept, and of course, it also measures the dimension in one of the directions. So, you can take a same object, rotate it multiple ways and throw dots at it and see what is the distance between the 2 extreme contours of the particle, and that gives you again an idea about the shape of the particle. The third one, shape comparator, is basically a way of translating the data that you have obtained from the first 2 methods into terms that describe the shape in a qualitative fashion. For example, you can actually define the bulkiness of an object as by a ratio. For example, you can say that if it is a perfectly spherical particle, my intercept length would be the diameter, right. Whereas if you have a non-spherical particle, then the length of my intercept will be different for different angles of incidence, and I can actually then represents the bulkiness of the particle by the ratio between the intercept of the real particle versus the intercept for a spherical particle. Conventional terms like flatness, for example. What is flatness? Flatness is a representation of shape, right, how flat an object is. How do you measure, how do you define flatness? You can say that flatness is essentially T by L, where T is the thickness and L is the length dimension. As I mentioned earlier, breadth to length or length to breadth is a good measure of the elongation ratio. A perfectly elliptical particle would have much larger elongation ratio compared to a spherical particle, for example. Sphericity itself is one of the key shape metrics. These are all called shape comparators, by the way: flatness, roundness, sphericity. There is something called rugosity, which is a representation of how smooth the surface is. For example, you can take the ratio of the perimeter of a particle excluding all the roughness and take the perimeter including all the roughness elements, and this ratio actually is a representation of how rough the surface is, which is a measure of the rugosity of the particle. So, the higher the ratio, the greater the rugosity or the rougher the particle is. So, all these are called shape comparators. So, they are a way of expressing in words what the numbers are telling you, and these apply specifically to single particle analysis. So, how is this different from a bulk property analysis? By the way, as chemical engineers working in process industries, most of the time you will be doing bulk analysis, not individual particle analysis, which is more for scientists, researchers. And the way this works is you actually measure shape based on its effect on some functionality. For example, let us say that you have a powder that you are trying to pack into a bottle, right. Compressibility is a major parameter, porosity and compressibility, which go together. So, what you would try to do is measure porosity as a function of compressive force, and it turns out that compressibility is actually a measure of particle shape. You can imagine that if you have an assembly of particles that are all uniformly shaped, let us say they are all spherically shaped, the way they would compress or the porosity that this population of particles would have would be very different than if you had a set of highly irregularly shaped particles. So, simply by looking at how the porosity of the sample changes based on a compressive force, you can assess how non-spherical the particles are on average. Another measure that is frequently used is called the tap density. A guy called J.K. Beddoe came up with this method. He designed an instrument called the Rho Tap. The idea here is, let us say that you pack a powder into a test tube or a beaker, you measure its bulk density, okay, and then you tap it using a hammer. It kind of the beaker keeps rotating and the hammer keeps tapping in a very controlled manner, and you measure the density after the tapping. You take the ratio of the density of the powder before tapping to after tapping. What do you think will happen? As you tap, things become more dense, right? They settle and they conform, they fit into interstices, and so the difference in density will be significant, provided that initially the particles were assembled in such a fashion that there was a lot of empty space between them. So, the ratio of density after tapping to density before tapping is a measure of the mean sphericity of the particles in that powder. So, if you have again perfectly spherical particles, even before tapping they would have settled in a reasonable way. So, the ratio of before to after would be close to 1, whereas if you had initially a population of highly non-spherical particles, the way they fit into each other would be highly non-uniform, and many particles would tend to settle when you do the tapping, right. So, that is an example of a functional measurement of shape distribution in a particle population versus trying to measure each particle separately. Another example of how you would do this is, let us say you are looking at flowability. So, you have again a set of particles, and in your process you have to make them flow across a tube from one location to another. You can look at the resistance to flow, you can look at the pressure drop, and these would again be indirect indicators of the shape distribution, because again a spherical particle distribution would behave very, very differently from a non-spherical particle population. So, the bulk property method or the bulk powder analysis method relies more upon the functional impact of the shape distribution of the particles rather than on the shape of each individual particle. Alright, I think we are running out of time for today. I had hoped to complete the shape analysis description in this class, but we will carry it forward to the next class as well, and then we will start talking about size distribution. So, the material that I have covered is covered in lectures 3 and 4 from the particle characterization course. So, do take a look at it, it will give you more background details to what I am talking about, and so that can be your exercise for your first Thursday class. So, Monday when we get back together we will quickly review some of the material in those 2 lectures, and then we will go further in the course. Any questions? Okay, see you Monday.